Good afternoon, everyone. First and foremost, I want to thank the Science Feder for the International Research Awards on Quantum Physics and Quantum Technologies. My name is Dr. Etido Inyang of the Department of Physics, National Open University of Nigeria, Abuja, Nigeria. I will be making a presentation on the topic analytical solutions of the N-dimensional Schrödinger equation with modified screened Kratzer plus inversely quadratic Yukawa potential and thermodynamic properties of selected diatomic molecules. I'll start by introduction. The Schrödinger equation is significant in quantum mechanics because the eigen solutions reveal vital information about the quantum systems for a particular quantum problem. The analytical solutions to this equation are used in describing the underlying basis of a quantum system. The exact and approximate solutions of the Schrödinger equation have been solved by many scholars. However, because exact solutions are few, many solutions have been obtained approximately. The approximate solutions to the Schrödinger equation for various potentials and analytical methods such as the supersymmetric quantum mechanics method, the asymptotic iteration method, the Laplace transformation method, the Nikiforov-Uvarov method, the NU functional analysis method, the series expansion method, WKB approximation, and so on have been studied by several authors. In recent times, the study of the atomic molecules with diverse single and collective potentials has interested scholars. For example, Inyang et al. Studied some selected diatomic molecules with the combination of Eckert and Elman potential functions. They observed that for each vibrational quantum number, the energies increase with an increase in the rotational quantum number. Obogo et al. Examined some diatomic molecules using Q-deformed Alton quadratic exponential type potential. It was observed in their findings that as the principal quantum number increased, the energy eigenvalues also increased. Also, Edet et al. Calculated some diatomic molecules using Dengfang plus Eckert potentials and the Poisson submission approach. The energy spectrums for a set of diatomic molecules of different values of the real vibrational quantum number were obtained. Furthermore, Inyang et al. Studied the Schrödinger equation, solved the Schrödinger equation with the superposition of Alton plus screened Kratzer potential using the Nikiforov-Uvarov functional analysis method. The bound state energy and wave function were obtained in closed form by applying the Greene-Ardish approximation scheme to the inverse square term. The resulting energy equation was used to compute the energy spectra for 12 diatomic molecules. For numerous potentials, many researchers have also studied the thermodynamic properties of different systems. For example, Edet and Eckert studied the thermodynamic properties with shifted Dempfang potential using the Q-deformed superstatistics approach. The study of the thermodynamic properties with the modified Dirac delta distribution and different diatomic molecules was investigated. In 2006, Bergner et al. Proposed the well-known modified Kratzer potential, which many authors have explored in the literature. Also in 2021, Ecott et al. Proposed the screened Kratzer potential by adding the screening parameter to the standard Kratzer potential. Recently, Edet et al. Suggested the screened modified Kratzer potential. This potential was used in investigating interatomic interactions in two atom molecules. Another potential of interest is the inversely quadratic Yukawa potential, suggested by Amzavi et al. Onate studied the Klein-Gordon and Schrödinger equation with the inversely quadratic Yukawa potential. Since then, many studies have been carried out by researchers in relativistic and non-relativistic regimes with this potential. The aim of this study is to obtain the approximate analytical solutions to the Schrödinger equation with the screened modified Kratzer potential plus inversely quadratic Yukawa potential, and use the obtained energy equation to study energy spectra and thermodynamic properties of selected diatomic molecules. The combination of at least two potential models has the propensity to fit experimental data more than a single potential. Hence, this study, which is not in the literature to the best of our knowledge. The convective potential is of the form given in equation 1, where phi there is a screening parameter and the letters Q0 to Q2 are defined. D subscript E is called the dissociation energy. Q is the control parameter. R is the internuclear distance. R subscript E is equilibrium bond length, and V1 is the potential strength of the inversely quadratic Yukawa potential. Here we are going to look at the approximate analytical solutions of the Schrödinger equation with the screened modified Kratzer plus inversely quadratic Yukawa potential. So in this study, the NU method, that is based on solving the second order differential equation of the hypergeometric type, is adopted. The details are found in reference 58. And here the N-dimensional Schrödinger equation is given as equation 2, where R as a function of R is the eigenfunction, E is the energy eigenvalues of the quantum system, Q is the reduced mass of the system, H bar is the reduced Planck's constant. Of course, with the inverse square time, equation 2 cannot be solved exactly. Therefore, we introduce the Greene-Aldish approximation to deal with the inverse square time. This approximation term is valid for value of phi far less than 1, and is given as equation number 3. So upon substituting equations 1 and 3 into equation 2, and with the simplification of the mathematics, we obtain bound state energy eigenvalues of the collective potential as given in equation 4. And the total wave function of the collective potential is also given as equation 5. Thermodynamic properties. The partition function is an important thermodynamic quantity that allows for the derivation of other thermodynamic properties of the system. Mathematically, the discrete form of the Boltzmann-Gibbs partition function can be expressed as equation 6, where k subscript b, lambda, and t are the respective Boltzmann constants, maximum quantum number, and the absolute temperature. Of course, at high temperature in the classical limits, the partition function can be represented by an integral given in equation 7, where lambda is the maximum quantum number. So equation 4 in a 3D can further be simplified as equation 8. Then using equation 7, the partition function can be expressed as equation 9. Then from equation 9, we use Maple software to evaluate equation 9. Then we have the partition function given as equation 10. Other thermodynamic properties are obtained from equation 11, 12, 13, and 14. That is, we obtain the vibrational mean energy, vibrational specific heat capacity, the vibrational entropy, and the vibrational free energy. Now, results and discussion. Here we carefully selected 4 diatomic molecules as with their spectroscopic parameters as displayed in table 1. Table 2 shows the energy spectra of the hydrogen, carbon monoxide, iodine, and nitrogen monoxide diatomic molecules when n equals to 3. So we obtain the bound state energies. Table 3 is the energy spectra of the selected diatomic molecules when n equals to 4. Table 4 is a comparison of our energy eigenvalues of modified Kratzer potential from previous studies. Table 5 is a comparison of energy eigenvalues of the screened modified Kratzer potential with previous studies. Table 6 shows the partition function of the molecules of hydrogen, carbon monoxide, and iodine at various temperatures. Now, discussion. In this study, the energy spectrum of equation 4 is used to investigate the energy spectra of hydrogen, iodine, nitrogen monoxide, and carbon monoxide diatomic molecules. The spectroscopic data for these molecules are shown in table 1 and we are collected from references as shown. These diatomic molecules were chosen based on numerous applications and studies conducted by various authors. The numerical value, energy eigenvalues of the combined potential for the selected diatomic molecules at various quantum numbers n and l are presented in tables 2 and 3. For a fixed value of principal quantum number n and the number of dimensions, the energy spectrum increases as the angular momentum L increases. However, the energy eigenvalues were found to be higher for n equals to 4 than n equals to 3, implying that the higher the order of dimension, the higher the energy eigenvalues of the system. Our newly developed potential models reduce to special cases of screened Kratzer and modified Kratzer potentials by applying certain boundary conditions to validate the mathematical accuracy of our analytical calculations. The energy eigenvalues for the special cases were also determined, and their numerical computations are shown in tables 4 and 5 for CO and NO diatomic molecules, respectively. The energy eigenequation of the special cases agrees well with previous research. Table 6 shows how the partition function varies with temperature for hydrogen, carbon monoxide, and iodine diatomic molecules. The results show that the partition function of 3 diatomic molecules increases with increasing temperature. This prediction can help engineers in the industry because hydrogen, carbon monoxide, and iodine are vital gases with numerous applications in industry and technology. Conclusion. In this work, we presented the approximate analytical solutions of the N-dimensional Schrödinger equation with the screen-modified Kratzer plus inversely quadratic Yukawa potential using the NU method and the Greene-Aldrich approximation scheme to the centrifugal term. The energy eigenvalues acquired were used to investigate 4 diatomic molecules such as hydrogen, iodine, nitrogen monoxide, and carbon monoxide. We have deduced potentials such as modified Kratzer and screened modified Kratzer potentials from our combined potential and obtained their respective energy eigenvalues equations. The energy spectra of NO and CO are compared with those in the existing literature and are in excellent agreement. The partition function and other thermodynamic properties of the selected diatomic molecules were determined using the energy equation, and the comparative behavior of these properties is presented graphically for the hydrogen molecules. Also, the partition function for these diatomic molecules were computed at different temperatures. The results show that the partition function of the 3 diatomic molecules increases with increasing temperature. This prediction can help engineers in the industry because hydrogen, carbon monoxide, and iodine are vital gases with numerous applications in industry and technology. All references can be found here. Thank you.